Okay, so let's see, what are we talking about first here? Let's first go over quiz 4 quickly. I just want to remind everyone, exam 1 is up now. This is the midterm exam. You take it just by clicking this link. You get one chance to take it, 75 minutes. It's open book, open internet, 15 questions. Make sense? It's very similar to the quizzes. So make sure you take it by Friday midnight. So take it anytime this week. The quiz 4 was some questions about the last lecture, sequential logic. The first question was, what is a true statement about latches and flip-flops? A latch is level sensitive. Flip-flops cannot be designed with an always statement. Okay, so a latch is level sensitive, right? Flip-flops cannot be designed with an always statement. That's not true. A flip-flop is level sensitive. That's not true because a flip-flop is edge sensitive, right? Multi-bit latch is called a register. That one's not really true. I mean, that one's kind of splitting hairs a bit, but a multi-bit flip-flop is called a register. I've never heard of a multi-bit latch being referred to as a register. And a latch cannot be reset. That's not true. You can reset a latch. What is the next state function of state bit 0 in the circuit below? To answer this, you just have to look at the next state function is going to be whatever's feeding the input of that flip-flop. So you just have to look at the input and then go backwards and figure out what the Boolean logic is. That makes sense? So it's going to be the current state of Q1 or the current state of Q0. Okay, and then ANDed with A. So I went ahead and just put all three next state functions on there. So Q2 is just not A, is feeding the input. Q1 is over here. That's Q2 and A. In the circuit below, suppose we set the A input to a constant 1 and then pulse the reset input. What is the state of Q2, Q1, Q0 in the third cycle? Recall that the S and R register inputs indicate set and reset. So the idea is that when you reset, you're going to set Q2 to 1, Q1 to 0, and Q0 to 0 because Q2 has a set and the other two have reset. So you're going to start out with 1, 0, 0. Does everyone see that? Okay, and then if you then just look at the next state logic, you can fill in the table for the next state of Q2, Q1, Q0. So, I should have kept that on there. But Q2 is not A, and A is hardwired to 1, so the next Q2 will always be a 0. And then Q1 is Q2 and A. A is hardwired to 1, so it's essentially just Q2, right? So the next Q1 will be the previous Q2. And then Q0 is Q1 or Q0 and A. And again, A is hardwired to 1, so it's essentially just whether it's just going to be set to 1 if there's a 1 bit in Q1 or Q0. So like I said, Q0 is going to get a 0. Q1 is going to be, man, I should have left that on there. Q2, right. So Q2 gets basically transferred over to the next Q1, and then Q0 is going to be the OR of the current Q1 and Q0. So 0 or 0 is 0, right? And then once you have those next states, you then drop them down into the current state for the next cycle. So you take that 0, 1, 0 and you bring it down to the next row of the table, and then I did have the next state logic on there, sorry. And then you recalculate your next state. So Q2 is always a 0 because A is hardwired. Q1 is the current Q2, so that would be a 0. And then Q0 is Q1 or Q0, which is 1. And so then you drop that down to the current state, and you calculate the next state, and it's not gonna change. It's gonna lock in at 0, 0, 1 because Q0 is essentially fixed because A is fixed. Q1 is the old Q2, and that's fixed, right? So there was just it took it a cycle to get to that steady state point, and then Q0 is essentially ends up being fixed too. So the value is 0, 0, 1 is just going to stay that way. Does that make sense? You guys with me? I didn't explain that very well, but the point of this problem is first you have to figure out the next state logic, which is just whatever logic is feeding the input to the flip-flop. And then when you build this table, you have to keep in mind that you have these three variables, Q2, Q1, Q0, but there's two versions of them. There's the current state and the next state, right? So the current state is the input to the next state function. So in the truth table, you're considering the first three rows as your input and the last three rows as your output. And then you always drop the next state down to the current state in the next cycle, right? So if you understand that, that's all you need to know for this. Okay? Okay, then in this question, I give you a finite state machine and ask what the output of the next state logic is for inputs S0 equals 1, S1 equals 0, S0 equals 1, and A equals 1. So in this case, if I say that S0 and S1 are the states, right? The state bits. So that means that we are currently in state 0, 1, right? Does that make sense? 0, 1, we're here, right? And then the input is A is the input and A is 1. So where are we going next? So if we're in this state and A is 0, then it says if we have not A, we're going to go to this state, right? So the next state's going to be 1, 0, right? So the next state for S1 and S0 is 1, 0. Does that make sense? Okay. Okay, and then consider the system Verilog module below. What's the problem with this design? This is pretty subtle. So you've got a module called FSM. You've got a clocked always statement that transfers the next state into the current state. And then you have a next state logic, which is combinational. And this is what's going to give you the next state as a function of the current state, and in some cases the input, like go, right? Go is an input. Make sense? So this thing it looks like it's just like a counter, right? Because it pretty much just, once you tell it to go, it gets it out of state 0 to state 1, and then it just kind of walks into state 2, state 3, and then back to 0, right? Does it? Oh, actually, well, that's the problem, isn't it? We don't actually tell it to go to state 0. We tell it to go to state 1, 2, and 3, right? Mm-hmm. But there's no setting the next state back to 0, so it gets stuck at state 3. So that's kind of a problem. But also the bigger problem here is that there's no default next state. Like this if statement this if statement doesn't have a fallback, like a default value for next state. So if this always activates, which it will, whenever any of its inputs change, and if none of these if conditions are true, then it ends up becoming a latch. So actually this won't compile because we said always comb here. So the compiler will say you made a latch, but you told me it was combinational, so I won't compile. But on the other hand, if you had made this with always at star, which is another way to write always com, except it doesn't do that check, right? Then you would end up with a latch here. You guys with me? So a better way to do this would be to have a little default right above this if statement that would say next state equals 0, 0, right? So if none of these match, it'll by default go back to state 0, 0 on the next clock. Okay? And it would also create that wraparound. So it would end up going from, it would stay at 0 until you give a go signal, and then it would go 1, 2, 3, 0, and then it would stay at 0 until you give it the next go signal, right? That's how it would work. Does that make sense? Okay, and this one says you're designing an FSM to keep track of the mood of 5 students working in the digital design lab. Each student's mood is either happy, sad, busy, clueless, or asleep. What's the minimum number of bits necessary to represent these states? You need to store the state of all 5 students concurrently. So I got this question from the book. It's kind of a conceptual question. There are 1, 2, 3, 4, 5 states? Yeah, there's 5 states. So normally you would need log base 2 of 5. So you need 3 bits. Except there's 5 students that you have to keep track of. So you would have to multiply the number of possible states is actually 5. What is it now? It would be, you'd have 5 possible states, right, raised to the 5th power, right? Make sense, right? Because you have to keep track. You have 5 students, and there's 5 states for each student. So the total number of combinations would be 5 raised to the 5th power, right? And then you'd have to take the log base 2 of that. You guys agree? Okay. I don't remember I don't have the answer for it on here, but it's whatever 5 to the 5th power, 12 bits. Okay, yeah, makes sense. 12 bits would give you up to 4,096 states. 2 to the 12th power. Okay, this says, consider the FSM circuit below. Which of the following describes the next state logic for S1? S1. So look at the input to S1, and it is an OR of something, OR of S0 or not S1. Okay, so you just look at the input and go backwards. Okay, any questions? Okay. Now I just realized that I don't think I ever finished the branch and jump lecture. We need that for the next lab. Yes?
Are the circuits active on the first cycle? Are the resets, are they active for the first cycle?
The reset the reset could be synchronous or asynchronous. Typically you would, you give it a reset pulse. And that would put it into what they used to call the sanity state when I was in school, the reset state. And so if you hold the reset for longer than a cycle, it'll keep it in that state. It'll ignore the inputs and it'll just freeze it, right? But as soon as you drop the reset signal, then on the following edge of the clock, whatever edge you're sensitive to, rising or falling edge, whatever you've got in the sensitivity list, then you'll transition on that first edge after reset is set to 0. Does that answer your question?
Yeah, just on because you specify it was rising and falling, or should we assume it's not specified?
I usually use rising, but it could be either one. Yeah. Sometimes you have a combination. Like remember in the test bench design I showed you, we actually use both edges. We use the rising edge to go to the next test vector and then the falling edge to validate the test vector. So sometimes, sometimes you use both clock edges, but generally normally I just use the rising. It doesn't matter if you use the rising or falling. It makes no difference. It's just whatever you want. Either way, you're getting, the clock period. You're changing state every, after every clock period. Okay, so I started talking about branch and jumps. I don't know if I finished this. So I mentioned that for the next lab, we need to add the B type and what was the other one? J type? J type. B type and J type. So this is different from MIPS. Much different from MIPS. Obnoxiously different from MIPS. This is really bad. Really bad. This encoding is terrible. So the branches and jumps both use PC relative addressing. So basically you put an immediate in there and that represents where you're going, like where the program counter is going to go next. That's the basic idea. There is a subtle difference though. I brought this up last time. In MIPS, the offset is the relative to the next instruction's address. So you guys have PC fetch, right? PC fetch is the address of the instruction in fetch, which is actually the instruction that's after the branch. So if you want to do that infinite loop thing, you know, the halt and catch fire thing where you just, the instruction branches to itself endlessly, then the branch offset would be -1. -1 meaning I want to go back 1 from the next instruction, which means me, the branch instruction, right? Whereas in RISC-V, they change that, and now the offset is relative to the branch instruction itself. So if you want to do the infinite loop thing, your branch offset should be 0, because 0 means branch to myself, right? So in other words, in MIPS, branch to yourself meant -1 offset, and RISC-V, it's 0, right? So it's a slightly different way to calculate the branch target address. You might say, well, how does this relate to this class? In the past, when we used the MIPS processor, or where we designed the MIPS processor, your program counter, you would use the PC fetch and just add the offset. That's it. But now you can't do that. You have to use, because PC fetch is the next instruction's address that comes after the branch in program order, right? Not in execution order, but in the order of your code. So you're going to have to add a delayed version of PC fetch. You're going to have to delay it by 1 cycle and call it PCEX, meaning the program counter address of the instruction, the EX stage, which is whatever PC fetch was in the last cycle, right? You guys with me? So you're just adding another pipeline register, that's all. It's not a big deal, but you have to make sure that you do it that way, because remember that we're getting the code from RARS. So RARS is going to calculate these offsets according to the labels that you're branching to. So in order for your processor to work with the code that's generated from RARS, you've got to make sure that you calculate your branch target correctly. Okay? Okay. Now the thing that's really bad about the B-type, I don't know why they do this. This is wild. So the B-type instruction format, I really hate this because I never can memorize this, but the B-type is a, it's not like any other format, right? Because they have the immediate, which is where you're going, the branch offset, right? Basically how many instructions you're skipping if you take the branch, right? That's essentially what that means. But that value is kind of spread all the way across here. So you've got bit 12 and then bits 10 down to 5 and then bit 4 down to 1 and bit 11. It's all over the place the way they encode these bits. I don't know why they do it this way. Also, the other thing that's weird is that in MIPS, that offset was the units of that offset was in terms of words, 4-byte values, right? Whereas here, the units are 16-bit values. So that offset represents a 16-bit address. Okay, so what that means is on a byte addressed machine, which is like every computer out there, you would have to multiply the offset by 2. Because all computers are byte addressed, except for the one we're designing. The one we're designing is word addressed, just to simplify it. So our program counter counts up by 1, right? And that 1 is in increments of 4 bytes. So we have to take the offset and divide it by 2, right? So in a real machine, you would multiply the offset by 2, but in our computer, we're just going to divide it by 2 because we want to convert it to a 32-bit address. So you start out with a 16-bit address, what I should say is a half-word addressable value, addressed value, a value that's pointing to 16-bit units of memory, right? And we have to convert it to a value that's addressing 32-bit units of memory. Does that make sense? It's confusing, but it's not a big deal because I'm going to give you the code for it just because it's kind of torturous. So I have this branch offset. I give you the code for it. Basically, this will assign a signal here called branch offset EX. Now, obviously, this is going to be a don't care if it's not a branch instruction being executed. You just ignore it, right? Your CPU will ignore it. So we calculate this for every instruction, even if it's not a branch. And I just have some bit twiddling stuff here that takes the bits from the instruction and uses them to construct the actual offset. And I actually multiply it by 2 by adding this 0 at the end, right? So I multiply it by 2. So this branch offset is the actual branch offset in RISC-V, convention, right? But then I have another signal called branch address EX, which then calculates the effective address, which is where you take the program counter EX. Again, this program counter EX is a new signal you have to add. It's the delayed version of program counter fetch. And I add it to the branch offset, but then I divide it by 4 by only taking it down to bit 2. So I concatenate bits 1 down to 0, which effectively divides by 4 and rounds down. Okay? And then you might say, wait a second, why do you have 2 bit 12s? That's the sign extension. So this is the sign extension. I have to sign extend 1 bit. This is assuming, of course, that your program counter is 12? 12 bits, right? You all use a 12-bit program counter? I think that's what we told you to use, right? Assuming it's a 12-bit program counter, you end up with an 11-bit branch offset when you do this. So you have to do a 1-bit sign extend. So these 2 lines of code, you can copy and paste these. The first line will calculate the real offset, and the second line will take that offset and add it to the program counter to give you the effective target of the branch. Make sense? Okay, so that's branches. Jumps are also very confusing. The J-type. Now remember, branches, just to make sure there's no confusion, branches have 2 registers, RS1 and RS2, because those are the registers you're comparing to determine whether you're going to take the branch, because branches are conditional. Jumps are unconditional, so if you go to the J-type, there's no registers in there. It's pretty much just they allocate all the bits. Well, there is one, sorry. There is one RD. There is a destination register, and that's for the link address. But there's no branch resolution. The jumps are unconditional. That's the difference between a branch and jump. So the J-type is an opcode, a 6-bit opcode. I should have said that. I don't know why I didn't put 6 on there. Yeah, the opcodes are all, 7 bits. RISC-V is 7-bit opcode.
0.
Yeah, 7 bits, sorry. To this day, I keep getting confused between MIPS and RISC-V. RISC-V is a 7-bit opcode, and then, of course, the RD is a 5 bits, right? So that's 12 bits, and that leaves 20 bits left over for just the offset, the jump offset. So we have a bigger offset for jumps, just like with MIPS. We have a 20-bit offset, but it's treated essentially the same way. You just add it to the program counter. You just have more bits. You have longer range. You have longer reach, right? Because you've got more offset bits in the J-type, you can jump farther away than you can with a branch. You guys with me? Okay? And then the RD field is used for linking. That's so you can get back to where you jump from. This is for like a subroutine. If you jump to a function, you got to get back, right? So that JD is used for program counter's got to go in there in the destination register. You might say, what if I don't want to link? You just put a register 0 in there then. Right? Like if you use a jump instruction instead of a jump and link, then the jump is treated as a pseudo instruction. It maps to a jump and link with register 0 being the link address, link register. Okay? Everyone clear on linking? Linking is just a return address, that's all. It just stores the return in the register file, the return address. Okay, what would be the return address, by the way? What is the return address? If I'm executing a jump, I want to return not back to the jump, but I want to actually go to the next instruction after the jump. So that would be the PC fetch, right? Right, yeah, PC fetch. Remember, we have 2 PCs now. PC fetch, which is the address of the next instruction, so that's where we want to link to. But now we're going to have PCEX, which is what we're going to use for calculating the branch offsets, just because that's the stupid way that RISC calculates branch targets. I don't know why they changed that. Okay? And now the bits are all scrambled, so again, I just give you the code. I'm just going to give you the code for the offset and the effective address, because I can't make rhyme or reason. It's like bit 20... Then they concatenate bit 20 with bits 10 down to 1. So the confusing part is that these bits in the immediate field are referring to the bits of the immediate, right? Which is not the same as the, no, it is the same. It is the same as the offset, yeah. This is the bits of the offset, which is the bits of the immediate. But then those correspond to different bits in the instruction. So I put these 2 tables together to try to clear this up. So for example, bit 31 from the instruction is bit 20 from the offset, because you see 20 is the first number there, right? But then bits 30 down to 21 of the instruction are bits 10 down to 1 of the immediate, right? So this table is what's mapping the instruction bits to the offset bits. And then this table just reverses them, and this goes the opposite, right? Oh no, this is, oh wait, I'm confused. Offset. I screwed this up somehow. 30 is 20, 19. Instruction EX. I thought I had this table reversed. I guess I screwed this up somehow. Yeah, I think I don't know what happened to that, but this code is good. Students have been using that code for the last few years, so you can just copy and paste those lines. Okay, any questions about that? Okay, so here's the one issue you have to deal with here that's a little different is when you encounter a taken branch or a jump, you have this problem where the branch instruction is going to be fetched, and then in the next cycle it's executed. But while it's executing, you're going to be fetching the fall-through instruction, whatever instruction comes after the branch or jump in the code, right? Now the problem is that the way the pipeline is organized, you're going to be calculating the branch target using the lines of code I gave you, and then resolving the branch. That's going to take a whole cycle. So you don't even know, what ends up happening is you don't know if you're going to take the branch, nor do you even know where you're branching to until the branch instruction gets to the very end of the time it's in the execute stage. At that point, you've already fetched, you've already nearly fetched the fall through. It's too late to do anything about it, right? So in other words, by the time you know where you're branching to and if you're going to branch, you've already fetched the next instruction in the pipeline. So the only thing you can do is to kill it, is to replace it with a stall. So what ends up happening is when the branch then goes to the write back stage, the fall through is going to, the fall through instruction, which is not supposed to be executed, right? Because you're supposed to branch. It's not supposed to execute the next instruction. It's going to be in the execute stage, but we'll have replaced it with a stall. So it'll act like a bubble in the pipeline. And then at the same time, we'll be then fetching the target instruction. So your pipeline executes one instruction per cycle once the pipeline is filled, right? Once you get the pipeline all filled up, then new instruction rolls off every cycle. Except when you start doing branches and jumps, those are going to be followed by bubbles, by stalls, so you're going to end up executing no ops in the pipeline, and so the throughput, your instructions per cycle are going to go down, right? You're not going to have one instruction per cycle. It's going to be less than that, depending on the frequency of the branch instructions, okay? So how do you implement the stall? Well, I think I mentioned to you that in MIPS, a stall instruction was all zeros, right? 32 zeros, that was a no-op, right? But they changed that in RISC-V too. In RISC-V, the no-op is not all zeros. There's actually some 1 bits in there, right? But it turns out it doesn't matter what it is, because a better way, we figured this out over the years we've been teaching this class. Instead of trying to actually put a no-op instruction in the pipeline, because that's way too complicated, an easier way to do it is just to have a flag in the pipeline called stall. So you would have one in the fetch stage called stall fetch, and you have one in the execute stage called fetch stall EX, right? And you just use that flag to indicate that whatever instruction is in that stage, yeah, just ignore it. Don't do anything. I mean, execute it, but don't like write it back. Don't allow it to branch. Like just render it inert, right? That way you can fetch the fall through instruction, but then you just have that stall flag there saying, yeah, don't do anything with this thing. You guys with me? Okay, but you have to be careful because this is where you can run into a combinatorial loop, because your control unit is going to be, inside your control unit, you're going to be executing the branch or the jump. And the control unit's going to put that stall signal out, right? But you have to make sure that the control unit doesn't see that stall signal until the next cycle. Because if it sees it immediately, then it's going to stall itself, and then it's going to say, oh wait, I got a branch, stall. Oh wait, I'm stalling. It's not a branch. Don't stall. Oh wait, I got a branch now again, stall. And you're going to go into a loop, right? You're going to turn into an oscillator, right? So what ends up happening is that the control unit sees the branch instruction, the jump, and it puts out the stall fetch, right? So its output is called stall fetch. It'll have an input called stall EX, which will be the delayed form of stall fetch. So you'll have a pipeline register that takes as input stall fetch and has an output called stall EX, right? The control unit will then use stall fetch as its output and stall EX as its input. So basically what the control unit is going to say is, note to self, in the next cycle, treat that like a stall. It's like sending itself a message for the future, right? So it'll set stall fetch. Next cycle, it'll become stall EX, and then the control unit will be reminded that in the previous cycle, it said to stall, right? So that's all you got to do with that. So you basically have, if this is the fetch stage, ignore this for a second. You have this little register here, flip-flop. It's only a single bit. Out of the execute stage, out of the control unit, you have stall fetch. That's an output from the control unit. It's going to go into a delay, and then it's going to feed back as an input to the control unit, which is in the execute stage. You guys with me? Okay. Be careful with that. You got to have that in there, or model sim it'll either lock up or it'll say iteration limit, reached and fail. Make sense? Okay. So the only other thing you have to add is in your fetch unit, which, we gave you the fetch unit. It's essentially that always state, that always block. You have to add those address calculations, right? So I've given you two of them so far. I've given you the branch address EX and the JAL address EX. That's the effective address calculation from the B type and the J type instruction. It's just combinational, but you're going to feed those in to a MUX along with PCEX to figure out what the next program counter value is. Okay? And then there's a fourth one I haven't talked about yet, jump and link register. So there's another instruction called jump and link register, which is just an R-type instruction, but that allows you to jump to an address that's in a register. So I think it's the RS register. So read data 1. Whatever the program, the register file gives you as read data 1, that's this. Except 12, not all 32 bits of it, just 12 bits of it, right? Because the program count is 12 bits. This is so you can return from a jump and link. You guys with me? So now there's 4 possible addresses that will go into the next program counter fetch. It'll either just be program counter fetch plus 1, or it'll be one of these 3 addresses that come from your execute stage. Make sense? So in terms of this, actually, once you have this infrastructure, and it's really simple, because then in your control unit, all you got to do is when you want to branch or jump, all you have to do is set PC source EX, which selects this MUX, set that and set stall fetch to 1, and you're done. That's all you got to do, and everything else will be taken care of for you. Of course, the program, the control unit needs to determine, if it's a branch or jump, and if it's a branch, whether it should be taken. So you'll have to do branch resolution. But the actual mechanics of taking the branch or jumper is very simple. It's just set that 2-bit signal, set that 2-bit signal, and set that 1-bit signal. Okay? Make sense? Okay, so this is the changes. So let's see. Yeah, the changes to the EX stage and write back. Oh, sorry. One thing I forgot to mention here. The program counter, I mentioned this earlier, but the program counter fetch has to have its little delayed, has a delay in there to create program counter EX. So we've added this MUX and these connections and these 2 registers. This is a single bit register, a flip-flop, and this thing is a 12-bit register. Okay? Okay, and then the write-back logic has to be changed slightly. You had a mux that was controlled by reg select, and it was a 3-input mux. You have to add a 4th input now for the program counter EX. So this is for writing back the link address, right? So that's not a big deal because you don't have to extend the size of reg select's 2 bits. It stays 2 bits because, you know, it was we kind of get this 4th input here for free in the sense that we don't have to widen the reg select signal. Okay, so you set the reg select signal to 3 if you're doing a jump in link. Okay. Okay, so to summarize all that, you add the branch address, JAL address, and JALer address. So those are 3 signals, 3 logic declarations. And you put the code in that I gave you for the jump and the branch address calculation, and you add them as possible next state values for PC fetch, meaning that you add an if statement in your branch logic, which will create a mux. Your fetch logic. And then you have to add a PC source EX. You didn't have that before, right? Because the program counter always just added 1 all the time, right? Now you need a PC source that controls the PC mux, the next program counter. Okay, so you have to add that. You have to add the stall fetch and the stall EX, and add the program counter EX as the 4th input to the regdest mux. Okay, so there's not a lot of changes. It's fairly minor changes to the structure, and then you have to. The big change here will be in the control unit, but you'll just be adding, you know, if blocks to your control unit to deal with those new instructions. Okay, makes sense? And then for resolving branches, how do you resolve branches? Well, first of all, what are the branches? What are the branches? What are the lists? Do we have a list? Yeah. So we have branch equal, branch not equal, branch less than unsigned, branch greater than equal, branch greater than equal unsigned. By the way, I think most of these were pseudo instructions in MIPS, but these are all now real instructions in RISC-V. So how do you resolve them? Meaning, how do you determine whether they should be taken? Well, you use the ALU to do it. It's not doing anything else anyway, right, during a branch. Right? You might say, wait a minute, isn't it adding the program counter to the offset? No, we have a separate adder in there. That code that I gave you to put that in, when you put that code in, it's going to create another adder, 12-bit adder. That's not the same adder as the ALU one. Does that make sense? So your ALU has a 32-bit adder in it. We can use that to do resolution. So you can use the subtract instruction for testing equality. So if you have a branch if equal in the execute stage, you tell the ALU to subtract, and if the result is 0, then you should branch, right? Because if the values are equal and you subtract them, the result is 0, right? And then you just use complementary logic for the branch if not equal. And then for these 4, less than, greater than or equal to, well, there's no greater than, luckily. There's less than and greater than or equal, right? Well, why do I say that? Because we have an ALU operation for set on less than, right? It gives you a 1 if A is less than B on the ALU inputs. If you want to know if A is, and there's a set less than unsigned too. There's an unsigned version of it. Those are 2 different ALU opcodes. If A is not less than B, then it must be the case that A is greater than or equal to B, right? So that's why you have these BG, BGE, right? If you had greater than, then we'd have a problem, right? If we wanted to test to see if A was greater than B, there's no ALU code for that. right? You'd have to like do a set less than and a subtract at the same time, basically. You'd have an ALU that would have to give you the 0 bit, but anyway, we don't have to worry about it, right? You guys with me on this, right? So basically what I'm saying is if you do a branch of greater than or equal, just use SLT and just do whatever the ALU, just do the opposite of what the ALU tells you, right? You just complement the result. Make sense? Okay. The other option too is if you had branch of greater than, you could swap A and B and do set less than, but then you'd need to have additional muxes on the inputs to the ALU, right? That would add hardware complexity. Okay, yeah, that's the control logic. I think I have some. Okay, so I have a test program for you for the lab. So this is a smaller test program than before because we're just testing the. There's only 2 jumps and how many instructions? 2 jumps and 6 branches. 2 jumps and 6 branches. So 8 new instructions. This tests all 8 instructions. So this gets a little confusing because what happens here is that if it's working, it's going to fetch the first instruction, fetch the second instruction, fetch the third instruction, right? Here. Branch if equal, 4 and 5. Are they equal? No, because I put -1 and 4 and 2 and 5. So that first branch instruction doesn't take the branch, so it should fall through. So it doesn't stall, it just goes straight to instruction 3, right? Which is a branch if not equal. That one should be taken, but remember that if it is taken, it is going to fetch the next instruction at 4, but that'll be ignored because it's a stall. So all the branches and jumps have a delayed action to them. They do take the branch, but it's 1 cycle late. So instruction 2, no branch. Instruction 3, branch, but delayed reaction. So we still get 4, and then we go to 8. Because why do we go to 8? Because that's going to target 3. Target 3 is at address 8. You see that? So
knows where to go back to then.
Well, no, that one actually doesn't. That one doesn't. That one doesn't have a link because it's a branch. Eventually, you'll get to this jowl that will link. Okay. Now, notice that this jowl doesn't have a register listed there because it uses. I think the default register for link is 1. Right. But it doesn't matter because we never execute that instruction. If you look at the fetch sequence, 5 is never actually executed. We always skip that. We always end up jumping over that one. We fetch it here, but it's a stall. Right? We do fetch it once, but we don't execute it because it's a stall. But I think the default write back in RISC-V is 1. In MIPS, it was 31, right? If you remember from MIPS, it was the link address was register 31. Okay, and then it just continues like that. It gets really complicated though, because it's gonna, kind of skip around in there. But this is what in order to know if the test program's working, all you have to do is look at your PC fetch and see if it matches this sequence, right? So you're looking for a time series sequence. This is what the address should be in each cycle, right? It's a sequence of fetches. Of course, when I say stall in parentheses, that means that the program counter is 9, but then your stall EX should be set, right? Is it set in that cycle? No, it will be set when PC fetch is 9, or sorry, PC EX is 9, right? Yeah, sorry. So let me clarify that. So this is, well, you can look at PC EX too. It doesn't really matter. It might be easier to look at PCEX because PCEX is the address of the instruction being executed. So you'll still get the same sequence here. But that way, you could look at the stall. Of course, you could look at the stall fetch too. Sorry, you could look at so you can either look at PC fetch and stall fetch, or you can look at PCEX and stall EX. Either way, that'll allow you to just track and make sure that it goes through this sequence, right? If it goes through that sequence successfully. Eventually it'll get to the end, and once it gets past the end, it'll just keep going. Yeah, so 13 is the last instruction. 14 is just a label. There's no instruction there. So it will actually execute from 14 on just forever, but you have X's in there, and your instruction memory will be empty at that point, right? You guys with me? So it'll eventually scoot off the edge of the program, but this should be how it begins. Okay? All right, so now once you have that done, then you can write you can actually take your square root program now. Your square root program hopefully will not have any instructions that you don't have implemented. Hopefully. It shouldn't. If it does, you'll have to fix it, right? So your square root program should work. So we want to combine your square root with your bin to hex. So we want to grab a value from the switches, treat it like an integer, right? So in other words, treat it like all the fractional bits are 0. So you get an 18-bit value from the switches. You're going to basically shift it to the left by 14 bits, right? To add the zeros. So to add the .0000, right? Right? And then you want to feed it into your square root program, calculate the square root, and then print it on the hex displays in decimal. So you'll have you'll have designed the software and the hardware for a calculator that can calculate the square root, right? Now the only caveat here is that your input is an integer, but your square root's probably going to be a fractional or square root, most likely, right? So you have to be able to display a fractional, base 10 fractional number on the hex displays. You guys with me? So there's 8 hex displays, and you know the square root's going to be between 0 and 511.9999, right? Is that what it is? Yeah. Like, if you put all the switches up and you give it its maximum input, it's like 262,000 something. If you take the square root of that, it's 511.99, right? So you're going to have 8 hex displays. You're going to allocate the first 3 hex digits as your integer digits, base 10 digits. And the other 5 will be your fractional base 10 digits. So you're basically going to use a fixed point base 10 number, right? Just pretend there's a decimal point after the 3rd digit. There is a decimal point after the 3rd digit, but those guys didn't wire they didn't wire it. We can't light it up. We can't illuminate it. But it's actually in there, but there's no wire from the FPGA. They didn't put a wire on the circuit board between the FPGA and the decimal point on that 3rd digit.
We got to cut costs somehow, man.
Yeah, that's exactly what they did. They cut costs. So you just have to pretend it's on. You guys with me? Okay, so you might be wondering then, final question is, how do we do fixed point in base 10? Easy. All you got to do is you'll have your square root with 14 fractional bits. You just have to multiply it by 100,000 and then convert it to decimal when you're done. That's all you got to do. By multiplying it by 100,000, you're effectively, shifting it to the left. Right? You guys with me? 1 digit, right? Kind of like when you calculate tip at a restaurant. You divide by 10, you kind of shift the decimal point, multiply by 2, get like a 20% tip. This is the opposite. We're actually multiplying it by 100,000, right? Guys with me? Okay, so that's all you got to do. So the objectives of the lab are to add 1, 2, 3, 4, 5, 6 branches and 2 jumps. So once you have those in addition to the other instruction, you should have all the instructions that you had in your square root program. In fact, if you run GCC on a RISC-V cross compiler, you'll probably be able to execute anything that comes out of GCC. I haven't done this with RISC-V. We did it with MIPS though, in the old version of the class. We actually ran a GCC that emitted, MIPS code, and we had, it generated the instructions that we did in class. So yeah, you have a pretty good instruction set. You don't have all the instructions, but you got all the most common ones, right? And then you want to test with the test program and then write a MIPS program that computes the square root of the value on the switches and deploy it on the DE2. So you flip your switches and you should see the square root value displayed within 100 instructions that are executed in 1/50 millionth of a second. Okay? Any questions about that? Okay. So the, let's see here. Yeah, and that's what I just said. Okay, the lab sheet is on Dropbox where we have this described in excruciating detail. And we have the grading rubric on there. And we also have the instructions, all the descriptions of the instructions. Okay? All right. So we're actually a little bit ahead of schedule compared to normal. So you basically have until almost the end of the semester to do this. 5 weeks. Okay, so, but if you're planning to do the lab, now remember, you have the option to opt out of this lab because the grade for this class adds up to like 117.5%. So if you're confident that you're going to do well in the final exam, then
Who said I was going to do well?
you can opt out of this lab if you want, right? In which case, if you really feel uncomfortable with the lab or if you have a bad partner or whatever the case may be, right? Or if you do well in this lab, you don't have to take the final exam, right? So this way you can customize the course to be more applied or more conceptual. The final exam will have a lot of conceptual material on it. I'm going to talk about timing analysis and CMOS design and digital building blocks. So for the rest of the semester, I'm just going to cover theory, basically. I've finished with all the applied, practical material that you need to get the final project done, which is going to allow you to say, if you do this project and when you're interviewing, you can tell whoever's interviewing you that you built a RISC-V CPU from scratch. Yes?
Why are you looking at me?
So I had the question about how I was dropping. If we decide to do both and do mediocre on both of them, will it be an average?
Yeah, yes, it will. Yeah. We just all we did is we used to try to physically drop a score, but now we just have the total be at a 117.
That's what I plan on doing mediocre on.
Yep.
Yeah.
Yeah. Okay, so I'm going to move on to the next topic here. We have about 10 minutes left, 18 minutes left. Okay, so the next topic is timing analysis. This is something that I should have, well, part of the problem is that when you guys deploy your circuits on the FPGA, you're kind of missing a lot of what's going on. The place and route tools are trying to make your circuit work at the clock speed that you want it to work at, which in our case is 50 megahertz. Usually, it's not too hard for the CAD tool to do that. That's why it only takes like 4 minutes or so to compile, which is really great. Because normally, if you have a larger design and you're trying to meet a faster clock rate, it takes a lot longer to compile a design for an FPGA. But we've with these Intel tools and this FPGA and the clock that we're at, it's really nice that you guys can iterate pretty rapidly, right? You can do like a 3 to 4 minute compile, right? But like I mentioned, the job of the synthesizer is to meet timing requirements. So you have this timing spec. The timing spec of our CPU is that it has to run in 50 megahertz, which means the worst case delay inside your CPU design, and when I say delay, logic delay, is 20 nanoseconds, the reciprocal of 50 million hertz, 50 megahertz, right? So the timing spec is basically how fast the circuit has to run. So now when you simulate, hopefully you guys are simulating. I know some students in this class, they just test their design on the FPGA, which you can do, but that usually involves more trial and error because you can't, there's less visibility. You have less design visibility. Unless you use like signal tap, but then signal tap requires you to put those probes in there and recompile every time you want to add a new signal to your list of probes. Simulation is nice because it's fast, but as I mentioned, the simulator is not showing you a realistic view of what the actually hardware will give you because the hardware has delays in it, right? And Simulink is assuming that the circuits are infinitely fast, right? So there's no delay between, Simulink doesn't show a delay between when an input changes and when the corresponding output changes. So, because it's just behavioral, it's just you're testing functionality, you're not concerned about timing when you're doing a model sim simulation. But there is a delay in reality. If you have a gate, you have an input change and you'll get a corresponding change in the output, and there's that delay. The delay is usually measured from the time when the input gets halfway from 0 to 1 or 1 to 0 to the time that the corresponding output goes halfway between 0 to 1 or 1 to 0, depending on what the transition is, right? Now, obviously, sometimes you can change an input without the output changing, right? So this is assuming, of course, that the output is changing in response to an input changing. You guys with me? Right? Like does that make sense? Like if you have an AND gate and one of the inputs is 0, it doesn't matter how you change the other input, the output will always be 0, right? But if you change the input and there's a corresponding change in the output, there's a delay there. That delay is caused by the resistance and the capacitance. It's the product of resistance and capacitance, RC delay. So there's actually two delays. There's the propagation delay and contamination delay. The propagation delay is the point at which is the longest delay possible. So the propagation delay defines the point at which the output is not going to ever change again. It's stable. It's the time for the output to stabilize. So the time between, specifically, the propagation delay is the time between an input changing and when the corresponding output has been stabilized, right? Contamination delay, on the other hand, is the earliest point that the output can change. So in other words, the actual time it takes for the output to change is actually a range of time. That's from the contamination delay to the propagation delay. You guys with me on that? Now you might say, wait a minute, you heavily implied by the previous slide that there's just one delay. Well, this is what you see at any one moment of time, right? But in general, this delay is not a fixed number, it's a range. It's a range between the contamination and the propagation delay. You guys with me? Now, why are they different? Well, they're different because in a CMOS gate, I'll talk about this later, but a CMOS logic gate has transistors that are responsible for setting the output to 1. And they have other transistors that are responsible for setting the output to 0. Those are called the pull-up transistors and the pull-down transistors. You guys with me? It turns out those transistors operate at different speeds. So if your output is going from 1 to 0, it actually will it'll happen faster than if it goes from 0 to 1. Because NMOS transistors are faster than PMOS transistors. They switch faster. It's just it has to do with the semiconductor properties. Specifically the carrier mobility. The charge carriers inside the silicon lattice go at different speeds in those two different transistors. You guys with me? So in other words, if you have a gate and the output goes from 1 to 0, it'll happen faster than if the output changes from 0 to 1. So that's why you have this range of contamination versus propagation. But that's for a single gate. For a whole circuit, on the other hand, for a circuit, once you start assembling multiple gates and you want to calculate the contamination and the propagation delay for the whole circuit, that also comes from the fact that there are short paths and there's longer paths. So if I change this D input, then the output is only subjected to the propagation delay of this last one gate, right? But if I change A or B, it has to propagate through 3 gates before it gets to the output, right? You guys with me? So this is called the critical path delay. This is the longest path through the circuit, but there's also short paths through the circuit as well. Okay, so what ends up happening is that the contamination delay for this whole circuit might be really small because of this short path, right? Compared to the propagation delay, which has to go through the critical path. You guys with me? Okay? Okay, so let's see. Okay, so propagation delay is abbreviated T sub PD, and contamination delay is abbreviated T sub CD. You have to remember this because we're going to have a lot of symbolic names for this stuff. Okay, so we got our first 2 symbols, TPD, TCD. Okay. Okay, so let's revisit this circuit again. So the critical path delay, or the long path delay, the book uses, I think the book uses both terms interchangeably. Critical path, long path, same thing. It's going to be 2, we're looking at worst case delay basically, longest delay, 2 times the propagation delay of the AND gates. Right? Why? Because you have to go through 2 AND gates in series, right? Serially, right? Plus the propagation delay of the OR gate. So if you add 2 times the PDs of the AND gates and 1 of the OR gate, you get the total propagation delay. The contamination delay is when you look at the best case delay. So then you have to look at this short path, number 1, and number 2, you use the contamination delay for the short path. So when you're looking at the long path, use the propagation delay. You're calculating worst case. But then when you look at the short path, use the contamination delay, which is the best case. So the contamination delay of this AND gate is the overall contamination delay of the circuit. You guys with me? So you look at the shortest possible time and the longest possible time as a function of the topology of the circuit, right? And the CDs and PDs of the individual gates that you're going through, right? Okay, so I was trying to figure out like how many possible paths you have to go through with a circuit. How do you calculate? How many paths are there? Well, it turns out that the number of paths is going to scale up according to the inputs. So for every input, you have a path, right? But also, if you have fan-outs, meaning that you have a branch, you have a wire that goes to 2 different spots internally in the circuit, that will cause more paths. That will create more paths. So the number of paths is basically for each input, you add the total fan-out from each input, right? So A has 1 fan-out, which happens here. You see that? A is here. A fans out along this point, right? B has 1 fan-out because it goes through the same fan-out point, as does C, but D has no fan-outs. You just go straight through, right? So you add up, for each of the inputs, you add up 2 to the power of the fan-out that you have along that path of that input, right? So in this case, there's 7 paths through the circuit, which I have illustrated by making 7 colors, right? There's 7 colors representing the 7 possible ways you can get through the circuit, right? Now you might say, why do you care how many paths? Well, because you have to look at all those, when you calculate the critical path, to find the critical path, you have to look at the longest of all these 7, right? And of course, the short path is the shortest of all these 7. So it can get complicated when you have a bigger circuit to find these critical paths and short paths. Of course, I'm not going to give you any big ones to do by hand. Okay, now there's kind of this crazy thing that happens called a glitch when sometimes when you have unbalanced paths through the circuit, you can change an input, but because there was a fan out in that input, the input change propagates at different speeds through the network, through the circuit, right? And it can cause the circuit to actually go from like 0 to 1 and then back to 0 again, right? That's called a glitch, or from 1 to 0 and back to 1 again, right? The glitch happens because of these imbalanced paths, right? So in this example, the imbalanced path is due to this inverter here, because B fans out right here, right? And it goes through inverter, but then it goes this way. So you have a longer path for B here versus what you have for the other branch of B. You see that? Okay, so if the input to the circuit is, say, 0, 0, 1, 1. So 0, 1, 1, the output should be 1. And if I change B, B is the one with this weird, imbalance. If I change B to 0, right, then I'm going to go from this row to the truth table to that row of the truth table, which shouldn't change the output because both rows have an output of 1. It shouldn't make any difference. So if I set B from 1 to 0, you shouldn't change the output. But in reality, you're going to see a glitch. What you're going to see is the output will be 1, and it's going to glitch to 0 and then back up to 1 again because of this imbalance in B. So the reason for that is because you have B with 2 paths, and so when you change B from 1 to 0, if we look at these two signals, N1 and N2, these are these internal signals, you see that N1, actually N2, sorry, I should say, let's start with N2 because that's the faster one. So if B changes from 1 to 0, that's going to cause N2 to go to 0 from 1, right? Because there's an AND gate, right? So basically, what you're doing here is you're sticking a 0 into this AND gate, which is going to cause the AND gate to go from 1 to 0, right? Okay, so when that happens, that AND gate above it, at that point, was already a 0. Right? Because we assume that the new input to that AND gate hasn't caught up yet because it's being waylaid by this inverter, right? So N2 is going to go from 1 to 0, no problem. That's fine. That's perfectly normal. But N1 is going to lag, right? So what's supposed to be happening here is that OR gate had a 1 and a 0, right? And what we're trying to do is switch it to 0 and 1. We're basically trying to take we're trying to take both inputs to this OR gate and flip them, right? And do it in a way that's transparent. So the AND gate sees 1, 0, and then it's going to see 0, 1, and it shouldn't make a difference because the OR gate's going to put out a 1 either way. But because the one input on the OR gate changes faster than the other, you end up with a brief amount of time where you have a 0, 0 here into that OR gate. You see N2 and N1, right? So basically, the OR gate has N1 and N2, and they're flipping, but the second input, N1, is flipping a little slower, right? So you end up with this time where both inputs are 0, in which case the OR gate's going to put out a 0 temporarily until its second input catches up. Does that make sense? It's always kind of hard to explain but you get this glitch here, right? Like I said, you're trying to swap the inputs, but that inverter is causing a delay in the swap. So there you get the glitch there, right? Now, I don't know if you guys have noticed this, but ModelSim actually simulates glitches. You ever see those? Every once in a while, you simulate ModelSim and you see a glitch. I don't know how it determines whether there should be a glitch, but sometimes you'll actually see them in ModelSim. So how do you fix a glitch? You can actually fix glitches, but you have to add redundant logic. So basically, the book has this example in this case. You have the original circuit with, ignore this new gate for the moment. In the original circuit, you had the following Carnot map. You had basically two groups in the Carnot map, right? That were, so let me back up here. You guys remember from 211 that this circuit is a sum of product circuit, right? This is just a sum of product style. You have those inverters there that are just inverting inputs, right? So you can provide complemented forms to the sum of products. But it's a sum of products, AND gates feeding into an OR gate. So you can convert that circuit actually into the Carnot map, right? Where you got these two groups on the Carnot map that represent these two AND gates, essentially, right? Well, what ends up happening with that glitch is when you go from one group to the next, you leave one group and you enter another group on the Carnot map. That can cause a glitch. So to fix the glitch, all you have to, again, that B, remember B was changing from 1 to 0, right? So you're going from this part on the Carnot map to that part, this part, right? Because that's where B changes, right? So you're going from here. Because you're moving across those two groups in the Carnot map, you get the glitch. But you can add another term by enclosing those two cells on the Carnot map, which adds another AND gate, obviously, right? But that way, when you move, you're still moving within a group on the Carnot map, and that'll actually prevent that glitch from happening. Okay? You guys with me?
Yeah.
Now, do we really care, though? Do we have to do that? No, it doesn't actually matter. Because glitches usually don't cause a problem. Because when they happen between the contamination delay and the propagation delay. You know, because they happen in a range, right? We say that don't trust the output of any circuit from the contamination delay to the propagation delay, because that's when it's in a state of flux, right? It can change. You can get glitches in there, right? It's unpredictable. So as long as you ignore the output of all your circuits until after the propagation delay is over, then if there's a glitch, it doesn't matter. You just ignore it, right? But you have to make sure that you enforce that specifically. You have to constrain the propagation delay, right? And that's what the timing closure does on the CAD tools. And that's also called, there's a name for that. What's it called? The dynamic discipline. The dynamic discipline is when you make sure that you control, that you constrain, you limit the propagation delay in such a way that you know that you can ignore anything that happens happens before the propagation delay. You guys with me? Okay, so I'll talk more about that next week. Okay, so don't forget about the exam.